All right, good afternoon, everybody. We've got 4 slide sets that we're going to go through briefly, and I'm going to get to a particular section in each one. So we talked about wireless and mobility last time. There's more to learn. There's courses worth of stuff to learn on how the infrastructure is actually built to route phone calls as you move things around, and how do we keep track of you as you're doing things. One of the concepts that's important that I can't ever decide whether it's gaining or shrinking in popularity though. It's indirect routing, where instead of telling you where I've moved to, I will let the network keep track of that and forward packets to me that you continue to send to the original location. So this is like forwarding your mail or forwarding your email. Nobody has to really change things. So that concept's very important in particularly mobile networking, not just wireless. You can be fixed wireless, but this is when you're actually moving around. And one of the family of protocols that's out there to get this done is something called mobile IP. And it's got its own separate section in here. And so if you'll permit me a moment to kind of get to exactly the starting point for it, I'll walk you through it. So from the network's perspective, no mobility is mobile user, but using the same access point. So this would be like 5G internet access for your home from Verizon, or a Wi-Fi hotspot that you use for everything in your house. As far as the network's concerned, you are not mobile. A typical mobile user is one that moves from one Wi-Fi network to the next and uses DHCP repeatedly to reconnect. So they will shut off their TCP connections. They're okay with losing them. There's definitely a break in between. High mobility is one where you would like to maintain the connection while you're changing from one piece of infrastructure to the other, moving from underneath one cell tower to another cell tower. So the ongoing connections part is the killer. That's the one that's tough. So with a little bit of vocabulary, what mobile IP does is they've got this concept of a home network for you, where you have a piece of software running on a willing enable router called the home agent. And the home agent is going to be a conspirator in this menagerie, where you are going to continue to send packets, have people around the internet believe that you're still home. They are going to continue to send you packets where DNS continues to say that you are, which is where you're not at home. And the router will intercept those. So you basically negotiate with the home agent before you leave. You move to some other location, and you get a new address from that network, and you open a connection all the way back to the original one and say, hey, I'm over here now. And so that home agent software will take care of forwarding the software, the data for you. So in this case, the user still thinks you're over there. The home agent forwards it through the network back to where you really are, and then there's a way for you to get the instruction, the responses back to the user. It doesn't show enough detail in our textbook to kind of give you the nuts and bolts of it, including the fact that probably the reply to the correspondent may need to come through a different path back through home, like a VPN might be worth. And there's some pluses and minuses to this. One of the inefficiencies with it is you could be doing this around the world thing just to talk to somebody that's sitting 1 foot away from you. But that happens all the time anyway. That happens with WebEx. I'm sending all of my packets to Dallas to have them come right back to Houston again to somebody that's sitting right in front of me. So that's okay. The network is used to kind of dealing with those types of flows, and it can handle that type of structure. But mobile IP is an important concept of trying to figure out, how do I move around without forcing everyone to deal with it, without forcing all of the users to have to track me down, or without me having to constantly update DNS. There are other ways of doing this, though. One of the ones of doing it is to use a service of a company. They used to be free, and I think most of them are paid, modest fees, but paid now. And it involves installing a piece of software on your computer that taps the shoulder of this provider's DNS server every time your IP address changes, and it lets it know. And so their DNS server is the only one that really knows where you are. So if you need a name, if your computer requires a name so that people can connect to you with the name, like in a URL, then you need a DNS entry. And in this particular case, if you really do move around a lot, then you don't want anyone to ever cache your DNS entry because it could be invalid 1 minute after they got it the first time. So you'll turn off all the ability to cache. You'll ask people not to do it. And this server, this service provider will constantly give out your DNS without any help from anyone else. So that's another way to do it. $4.95 a month, something like that. And those are cool services to play around with, just to see how they work and what they do. It's good to Wireshark and see what's going on with them. But those are examples, alternatives to dealing with this service, which hides the fact that you've moved. Mobile IP really kind of hides the fact that you've moved. Okay, on to the next. I wanted to expose you guys to some material that was in a chapter of a book called Communications Networks by Alberto Leon Garcia, and he goes through, along with Indra Wajada, how to understand the various ways of encoding. So I'm going to give you enough of a walk through this to help you understand what's in this chapter, and for you to decide if it's something you're interested in enough to go and track down on your own. So basically, we want to turn things into ones and zeros, but those aren't the only choices that we have. We could use a variety of different symbols that we encode. What we have to decide that's more important is, are we going to send things in blocks of data at a time, or is it a continuous stream? Blocks would include files. Streams would include just what you might think, streams, like real-time voice and video, like maybe watching the Astros beat the tar out of the Twins again tonight. That would be a great thing to stream over the internet. So you can calculate transmission time, which is a factor of the delays that you guys have already seen this semester. You also can reduce the effort required by doing things like compression. And so they walk you through a little bit here of what compression is possible. But where it starts to get interesting is where they show you what's actually going on with these data streams. And if you've ever played with an audio mixer or an audio encoder on your laptop, then you probably have seen a graph that looks something like this, which is a waveform for speaking the phrase, the speech signal level varies with time. And this is a human's voice that basically is changing this sine wave pattern as it goes through. And they drew purple lines in here to kind of show you where the syllables or the letters are and things like that. What we have to do if we want to transmit this is digitize it from an analog signal into a digital signal. And so what we may do is come up with something that's just an approximation, but it's close enough that if you reproduce it from this estimate, it's good enough to tell who it is and what they're saying. That's kind of the goal. And there's actually an international standard, a numeric score you give to an audio feed that shows how well people are able to comprehend and find intelligible what's being said. And it's called a MOS score or a mean opinion score. There's whole books written on how to set those up and how to perform them and test them. I will tell you that having dug through in depth in what the Skype engineers did, that they were willing to publish publicly, they did stuff with as much rigor as I saw people at Bell Labs do. And I'm not an expert on what all people at Bell Labs do by any means, but it was very impressive, very scientific, and surprised me. Shame on me, but I didn't expect them to take it quite such a scientific approach to it. It was awesome to read, and its stuff's out there. So this is a field that's taken quite seriously. If you want to come up with a bit rate for a digitized signal, one of the fundamental rules that we learn early on is you can't send more bits than the bandwidth can kind of handle. So the faster the bandwidth, then yeah, the more data you can send. But there turns out there's a rule for actually getting that done that came out of the labs. So for a 4 kilohertz signal, you can get twice the amount of data off of that, which is 8,000 samples a second. If you have a 22 kilohertz signal, the rule is twice, so you can get 44,000 samples a second out of a signal that fast. So for a phone call, if we know that we want 8 bits each times 8,000 samples, then it's 64,000 samples per second. We can design a network to carry that for us. And for CD audio, we carry something else. So they walk you through a little bit of this. These are only the slides after all. There's a book to go along with this as well. They walk you through how to calculate some of the frame sizes and what some of the latencies look like and the amount of bandwidth that you need, which is kind of cool to see kind of the amount of bandwidth that's required. Then they talk about how do we now take this data that we've built it and actually get it transmitted over a communication systems. So they start with the fundamentals that no typical network book ever does, and they basically walk you through the channels that are available and the things that are working against you, impairments they're called, that make it difficult for you to get your signal across, like signal attenuation, the natural fact for it to become weaker the longer it stays in the channel. Signal distortion, the habit of signals to drift in frequency, all kinds of noise caused by heat. The hotter it is outside, the more noise is introduced into a cable. There's impulse noise with people sparking things with static electricity or something passing underneath. There's crosstalk because your wires aren't shielded. Your signal actually bleeds from one pair to the other. And then other types of interference like intermodulation noise as well. Early on, when we did analog long distance, we would periodically boost the signal, and I've drawn this for you several times before, and you boost everything, including the noise. You try to filter some of it off, but you basically have stones and knives and bear claws to kind of work with. It's analog. There's no digitization. You can't pick the original voice signal out. How do you know that that background noise that's annoying you wasn't there when they spoke into the phone? How you can't possibly know. But this worked well enough to make phone calls around the world. They talk a little bit more about the impairments. Here's one of my favorite things that they do in this book is they show you kind of graphs of what happens. So sent on the left and received on the right, you can see it's much weaker. But with digital transmission, what you sent on the left and received on the right is also kind of a mess. But can you still make out when it was above and below and then again above on the line? If you can, then you can reproduce the original signal. You really can't reproduce it up here. You can amplify it, but you end up amplifying the entire thing, noise and all. So that's kind of the beauty of it. So instead of using repeaters, we will actually be able to regenerate a completely fresh, pristine copy with the ones and zeros without any noise at all. And you can do that 1,000 times and go forever without any degradation having to be delivered to the end user. Then you can design this so there's very little probability. So how do we design a digital binary system? You could do something easy like make positive A voltage ones and negative A voltage zeros, but there's some real issues with that. Like what happens if somebody wants to send 1,000 zeros in a row? It looks like you've died. And one of the big problems with that is there's no change in polarity here to help you keep in sync with the sender's clock. Because remember, your clocks drift apart, just like two wristwatches. They are going to drift apart from each other. So you want to avoid any kind of encoding signal that permits no changes in the sine wave, that suppress the changes in the sine wave. So with pulse transmission, you want to maximize the rate to get things through there. So if you want to send a positive, it's with the electronics, it's going to end up looking like it does on the right. And if it's a narrow pulse, then the typical output is kind of spread out, as you can see, with this sort of bell shaped. You can do 2 times the bandwidth pulses per second, and we talked about that a minute ago. So the bandwidth of a channel, if it's a sinusoidal frequency, then the output is attenuated by an amount that depends on whatever that frequency is. So what you really want is perfectly is a channel that totally transmits exactly what you sent. And if you've got the ability, the electronics, you can do something called multi-level pulse transmission, which is pulse up for different strengths and have each of them represent a different value. And I'll show you an example, but I'm going to draw a little bit for you. If I can click on this thing correctly, get it to open, I'll draw a little bit for you as well. So what they're basically talking about is if you've got enough refinement and enough control over your signal where you can pulse up not just to this signal or not to the original full strength, but you've got the ability to actually pulse up to 3/4, a half, and 1/4, and you can do it in any combination you want. Then you basically are calling this one value, this another value, this another value, and so forth. So you're actually able to send 8 different values in a single cycle. If you can subdivide and manage the signal strength well enough, then you can get different amplitude levels across the wire. So that's a trick that we use to increase the amount of data that we send over bandwidth. Everything's got noise, so we do have to calculate sort of what the bit error rate is. So here again is an example of where I have high signal to noise ratio, a lot of noise introduced, and then I pull my signal out at the end, and I can still reproduce the original signal. If I have low signal to noise ratio and I have the same noise that's introduced, then I can have an error. So you've got to manage this stuff carefully. You don't go too far with your signals. Claude Shannon is the guy that came up with this channel capacity idea for Bell Labs, and basically they are telling you based on the signal to noise ratio, you need to mitigate your bandwidth on your wire down. The more noise there is, the smaller that ratio is. So that was hugely helpful, both in setting targets for what the signal to noise ratio needed to be to sustain bandwidth, and telling you when you needed to slow down because you have too much noise. The ratio is too small. So what that would do in this case, the way it would change this output and keep it from being ruined, is you would end up instead with maybe using this whole thing to be just a single value. And you might conclude this is a 1 even with this noise, down here, as opposed to trying to figure out, is this a 1, is this a 1, is this a 1, is this, and do it like they did, so you'll slow the bandwidth down. Okay, you can calculate sort of the average as you go along on these things, and they give you an example of some numbers. If you've got a telephone channel with a bandwidth of 3,400 hertz and a signal to noise ratio of 10,000, then you're going to be able to negotiate a modem connection that can do 45,000 bits per second. So that's a 40 dB change in level between a difference between noise and signal, which is really good quality line in my experience. So they walk you through the bit rate that you can get on some typical types of circuits based on that algorithm. So it kind of walks you through. And then they get a little bit more into detail. This is the last thing I'll kind of show you is how they draw out some of this stuff. What they're going to show here with multi-level signaling is a variety of waveforms. You can actually send more than one signal at a time on a circuit. And so what I showed you before was a little different version than this one. What they're looking at here are sending 3 signals: the light purple, the yellow, and the blue. There are 2 colors of purple on this chart. There's this one that starts like this, but the purple one now, the light purple sort of splits away, and that's one signal that you're trying to send. You have a yellow one, and then you have the blue one. And you can combine the 3 of them together, and when you do, you get the dark purple line. So it almost matches exactly here because there's really nothing going on. But as these other ones start to wake up and do things, the shape takes on its own form, and that's the one that you end up sending across the network. So noise will limit your accuracy. On the left, I figured out there are 4 signals, and on the right I've got 8 signals, but that noise is big enough, it's probably going to ruin the right-hand side example, so I might want to stick with the left. You need rules for how noise is distributed across a network as well, and you can design your network transmission protocols accordingly. All right, so let me skip ahead and find, oh, it was the next freaking slide. That just figures. All right, hold on. Getting too impatient. Line coding. So here are some examples of how to take a series of binary bits shown across the top and encode them. So on unipolar, ones have voltage and zeros do not. That's okay unless you have a long string of values. So if you want to use unipolar, you're going to have to pass your data through a piece of software that intentionally is going to mess with things to guarantee that there are changes in polarity, for example. Polar non-return to zero is the second one, and it does the same thing, but just never goes to zero. So with either ones or zeros, you at least have a change in the polarity to tell what the clock is on the other side, because he's only going to change things when his clock says to. So you can kind of keep time by watching how often he does it. You can have differential encoding, which basically means every time you go from a 1 to a 0, then you flip the polarity that you would use. So instead of being up, down, 1, 0 would be up, up. Or if you were already on down, when you got 1, 0, it would be down, down. You would stay down. So that gives you the third one. Then there's bipolar encoding. The more common ones that we use are the ones near the bottom. Manchester encoding is what's used on high-speed digital voice circuit lines in the world's telecom industry. And they are all there to kind of keep you from losing track of what the clocks look like. And spectrum of line codes, you can sort of measure the power density of these things and figure out sort of how stuff works. I've been trying to get Siri's attention all day long, and now she wakes up because of something I said that didn't at all sound like Oye City, whatever. So, and did it again. Now it hears me. So these have better, more details in them. We're not going to go through it here. I just want to give you an idea of kind of what's in here. The last thing they show you is how you can use frequency and amplitude modulation to actually encode those signals that we just talked about and kind of push them through. So here's phase modulation. It's a little hard to see, but when you finish the 1 and you do the 0, you flip the sine wave. So you're going up, down, up, down, up, down, up, down, up, down, up, and you do down 2 downs in a row. Can you see that? Here and here and here. You have the ways of doing that. So examples of modulation, you can sort of figure out what's going on that way. So it's the first time a lot of computer scientists will ever have seen exactly what's going on and what people are trying to, how this stuff gets encoded. It's all analog at the bottom, and I've told you guys that before. They walk through some spectrum stuff, but we've seen all of this kind of stuff basically before. They also walk you through cable modem management and stuff like that. All right, let me take one last peek and make sure there's nothing else I cannot live without in here. There's more stuff that deals with a little bit of the electronics of it. Dense wave division multiplexing, which is multiple colors of laser light on fiber. Error detection and correction. They walk you through more of parity checks and then CRC codes. They actually do a very good job of walking you through, and they try to show you that spatial distancing that I tried to describe, where you surround valid code words with invalid code words so you can't get tricked with simple errors. Binary polynomial math, that's how you get CRC codes done. So we've seen some of this stuff before. So it's an alternate textbook. It's more EE oriented, which is why not as many computer science departments use it, but you'll find more technology schools will use more of this material. All right, thank you for letting me kind of divert and show you a little bit of that. Okay, and this is one of the weeks where we end promptly at the bottom of the hour, maybe a few minutes before. So that's kind of why I'm going super fast here as well. I want to spend the rest of the time we have today on network security, and particularly sort of understanding what the definitions really mean. There's some really key important differences in what we mean when we talk about making the network secure. One definition is of confidentiality, where only the sender and the intended receiver should be able to decipher the message. So the sender will encrypt it and the receiver will decrypt it. So that's confidentiality. Authentication is one where you can be certain that the person who sent you the note is who you think it is or who they claim to be. And so that's another goal of sending information securely over a network. Message integrity involves making sure the message couldn't have been changed, either in transit or later. And then access and availability means it's got to be something that doesn't prohibit or restrict your use of the network resources. So there's a couple of fun examples I'll throw in here of things that I've had before, but the book does a pretty good job of walking you through some of these areas. Friends and enemies like Alice, Bob, and Trudy. Trudy is listening in, and she can intercept messages. The place where that really becomes an issue is when you try to do a type of an attack called a replay attack, where I just simply listen to all the packets going back and forth, and when they're done, I will repeat what Alice did the last time. If she started with a handshake, I will start with a handshake. Bob should respond the same way to me as he did to Alice if I've sent exactly what Alice did before. So you can make Bob do something twice that he thinks he's doing for one person, when in fact he's doing it for you. And so that's kind of dangerous, and it led us to do things like start with random sequence numbers to make sure that no one can, what are the odds that both sides are going to guess the same number again twice later. So that's the reason that will screw it up is because Trudy's acknowledgement numbers would then be wrong, for example. So that's one area where you have to kind of worry about this stuff really happens. You have people that imitate that they're the real DNS servers, or that they're the bank, or that they are giving you new routes because they are a router with updates, and those things aren't real. So what can a bad guy do? You can attack you with things like denial of service attacks. You can impersonate someone else, just simply listen, add additional messages into a connection that weren't really there before, like add an extra digit before the period for your bank balance, for example. Or you can take over a connection by stepping in and continuing the conversation when the user doesn't know that your identity has changed, and just cut the other user off, take over their MAC address, do something like that. So what has cryptography tried to do with this? And one of the most important inventions, one of the most important discoveries ever in cryptography for networking, eliminated the requirement to have two channels of communication, one for the message and the other for the passwords. I've had jobs where I was given a sheet of passwords to use, numbers, and every time I logged in, I would use one of those numbers and mark it off the list. So even if someone heard it, it would never work again, at least not except randomly. Those are one-time passwords. The problem is they can't send me the sheet of numbers I'm supposed to use as an email attachment that's not encrypted because I don't yet have the encryption key or the password. So you have to figure out another way to do it. When I worked at Rice's radio station as a student volunteer, they had this ominous orange, I think it was, a folder, cardboard folder, and you open it up. It's from the Federal Communications Commission, and it had instructions on what to do in case of a national emergency, which basically meant one thing and one thing only, which was the Russians hit the button. So you had a little envelope, and it had a couple of code words in it. And if your emergency broadcast radio, which every radio station, TV station had to have near a human being at all times, if it went off, you would open the folder, and if it said, look, an important message is coming from the President of the United States, here's your code word. If it matched what was on the inside of the envelope, outside of the envelope, you'd open it up, take out a little note card, and then they would have to tell you what supposedly is the secret word that you couldn't see without opening it. So it was really thick paper, for example. And if those matched, then at least you had a minute head start on evacuating the city from everybody else. I mean, at least you knew to rebroadcast the message and faithfully remaining at the radio station. But again, that required, they didn't send you those codes that they were going to use next month over the radio network. They sent them via the mail. It's a separate network. So really critical invention was one that prevented us from having to continue to have two channels of communication. For Cisco, I was assigned a piece of software that generated a seemingly random number every 60 seconds. And it started off as a physical card, but then it just became a little app on my laptop. And whenever I needed to log in, I would type in a keyword, number that only I knew, and into this little tool, and it would generate a number, and I would copy it and I would paste it into my VPN connection. And it was a combination of my password and some number and then their algorithm. And that changed every 60 seconds. So if I messed up my connection, I'd have to wait, half a minute or something on average to try it again. But that is a one-time password system, and that software had to be downloaded to me securely. I had to come into the office to get it on a secure network connection. So this stuff is the way the world has worked for forever, trying to do these encryption keys. And then along came Ravish, Shamir, and Edelman from MIT in oh my gosh, I don't want to lie on when it was. Was it 69? It can't be that long ago. I mean, time just, I've lost all sense of time. Let me see if I can find these guys. How about if I look for his name in a paper? There it is. I just saw it. 79. I was only off by 10 years. So this article, A Method for Obtaining Digital Signatures in Public Key Crypto Systems, changed the world, changed the way we did encryption. And these guys became very famous and very wealthy from doing this. There was a large successful company named RSA Security, and they may still be around or bought by somebody else. I can't keep track. Until maybe, 15, 20 years later, when the guys at the British version of the CIA, I think it's called M5, were given permission to publish what they had discovered, which was exactly the same thing, but years earlier. But they weren't allowed to broadcast it because it was a national secret. Happens. So you can either have fame or fortune, but you can't have both. I had a boss that told me that once. All right, so the way this works is worth drawing out. So I'm going to switch back to my tablet and draw for a little while. And I'm going to give myself a new space to kind of do this in. Okay, so suppose I have Bob and Alice, and they would like to send messages to each other. And the message they want to send is M. That's the variable that represents the message. And if Alice and Bob, which conveniently are A and B, want to send something, what Alice can do is pass the message through some sort of a function that will produce an encrypted version of that message. And then it is safe to send over the public insecure network. All right? And what will happen at the opposite end, obviously, is Bob will have some sort of a function that, given M prime, will give him back the original message. All right, with me so far. So the problem is, how does Bob know how to get this function? Because this function is a decryption key. And how do I do it without sending it over like through the mail or a separate deal? Well, you can try and email it to Bob, but there's just no way to do it. So what RSA came up with was a workable, clever alternative. And they use a pair of keys instead of just one key. So for each user, Alice, she has a public key, and Alice also has a private key. And Bob has a public key and a private key. Right? So public and private basically mean, is a managed switch the same thing as Let's come back to that in a minute. No is the short answer, but sort of is the right answer. Okay, so public and private key. So what I'm trying to do is to prevent people from stealing our stuff. So what Alice can do is do exactly what the name describes. You have a sort of a public registry, and you've got an entry for Alice and you have an entry for Bob, and Alice's entry contains her public key, and Bob's entry contains his public key. So what Alice can do is now encode the signal by feeding this algorithm her private key and gets an encrypted message out. And what Bob does at the other end is he takes the encrypted message and passes it with Alex's public key, which he has access to, and you get back the original message again. So there's three things I want to try to guarantee here. One of them is it really came from Alice. And another one is it's really Bob. And the third one is no one can eavesdrop. An alternate set of three would change these to only, let me see how I can figure this. I got to make this succinct or I'm going to run out of room here. Alice's public key only works if Alice's private key encrypted the message. And the same thing for Bob. Right? So those are similar ways of saying it's really Alice, for example. So the idea is anyone can grab Alice's key and it'll only make sense out of a message that was encrypted with Alice's private key. So she needs to hold on to the private key. But she doesn't have to worry about the whole world learning her public key. She will post it in a public place for people to see. And which one of these three does this accomplish? Well, you know it's really Alice. And people can sort of not eavesdrop unless they go and get your public key. If they know you are the one who supposedly sent it, then they can just go get your public key like Bob does, and they'll decode your message. So you can't really do the third one. And as far as the second one goes, anyone can decode this message. All they need is your public key. So it is not intended just for Bob. So it's not really just Bob that's going to be getting your message. All right, what else can we do? We could do the opposite. I could have Alice take a message and send it to Bob using Bob's public key, and then have Bob decode it back to the original message using his private key. And that'll work. So which of the three does this solve? Well, I know that only Bob can receive this message, so I get this one done. But anyone could have sent it to me. The encryption doesn't say anything about who really did the encrypting. All I know is my own public key that was used, but anybody could use my public key to send me something, and they can claim to be whoever they want. And as far as eavesdropping, yeah, maybe it's now hard to decipher the message, but it's still not all three. It's the bottom two. So I have one way that'll get me the first one, and the other way that'll get me the other two. Here's where super genius sort of pops into this design. One of the things that they made true was that encrypting a message with someone's public key and giving you M prime, you can take that, as we've seen, and decrypt it. So I'm going to draw the decryption a little bit different. This produces M prime, correct? So if I take this, which we all know is M prime, and I feed it back through the algorithm with C's private key, I should get back M. So start by encrypting it with the public key, then decrypt it with the private key, and you get back the message. What they also made work, which was really critical here is you could start with the private key. And that's going to give you an imprime, some sort of imprime. And you could decrypt it with C's public key, and you'll get back in. So it's unusual in that you can do it in starting with either key. So what that's going to let me do is solve both problems at once, because what I need is a combination of the two. One of them did this, the other two this. So what I'll do is take this message that Alice encoded with her private key and feed it into this nested function. So what I'm going to have is a pair of functions back to back. The first one takes the message and encodes it with Alice's private key. And then you're going to do it again, feeding the output of that as the input to the next iteration, which will use Bob's public key. And I will send that across. And what Bob will do is the opposite. But it doesn't matter the order he does it in. He can do it in whatever order he wants. And he can take this prime message and first decode it with his public key, and then, private key, and then with Alice's public key. So it's just a match set. I have Alice private and public, and I have Bob public and private. So what will this do? It means that when I receive the message, I can only decode it with Alice's public key, so it must have come from Alice. And I'm the only one who can finally decrypt it the rest of the way, because Alice used my public key to encode it as well, and only my private key will do it. So the only way I'm going to turn this message from gibberish into something is if Bob's private and Alice's public keys are in fact the two correct keys to decode this message. So this was revolutionary because people can publish their public keys. They don't need to worry about somebody stealing it from them, eavesdropping on them. And you can exchange these things at the beginning of a communications pattern. So for a web browser and a website, the certificate authority that you see at the top of the web page, like let me open mine up here, and we'll go to Google. I see the little lock, and it says it's secure. Oh, really? Who is it supposedly from? It is from google.com, which matches the URL. Okay, well, give me more information about this. So Google's big enough that they can authenticate their own certificates. Most of the time, people have to go to someone else to get it done. So what they're basically showing you here is that this service, Google Trust Services, has taken a look at what's going on here, and they verify that this is really Google. So here's the way it works. I connect to the website. I tell the other guy, let's go to a secure connection. So I upgrade to HTTPS if I don't start with that. If I don't start with that from the get-go. And in order to make that happen, I'm going to give the browser my public key, and I'm going to encrypt the page with my private key. And one of the things I'm going to encrypt with this page is my certificate. And the certificate is additionally going to be encrypted with the encryption authority's public key for me. So when I receive this bundle of stuff at my browser, I will use the website's stated public key to decrypt the web page. I will hand a copy of the certificate off to the certificate authority, in this case Google Trust Services, and hand them the encrypted version of the certificate that I was given. And only the certificate authority can decrypt it because it was encrypted with their public key. And they can look and see several things. One, they can see it claims to be from google.com in this particular web page, and that when they decrypt the certificate, it says it's also from Google, but they decrypted it very importantly with the private key that they had stored for Google certificate. So it'll only come back positive. And if they're happy, then they send a note back saying, turn the lock green. Okay, this really is who the URL claims it is. And my browser continues to decode the rest of the page using the public key from that website. All right, so I don't actually have to send a public key or maintain that type of thing quite the same way. So it's a variation, but it's quite elegant. So all you have to worry about is that the keys are good, and a lot of them aren't. And we've had lots of these encryption technologies come and go because they get hacked. And the expectation is, if you're going to show up at one of these security meetings or security conferences and expect to not be laughed out of the room or taken not seriously, you need to show up with something new, like I cracked one of your codes and here's exactly how I did it. So that's very useful to the security community, and then you'll be listened to after that. I can recommend some lectures, and I don't know if they're still out there or not, but Coursera used to have, I think it was Coursera, used to have a lecture from Dan Bonet at the Stanford Security Institute. He's a comp sci prof out there, one of the best lectures I've ever heard. Not because it's the most inspiring, but he doesn't make any mistakes and tells lots of interesting tales about how people have messed stuff up. So this one is free. He talks about public key cryptography in there. And basically what you're going to get out of a course like this is that security is multifaceted and very brittle. So if you leave a piece out of your security environment, the whole thing is going to come crashing down on top of you. And he gives lots of examples. I took the class for pay and took a couple of others with it as well. But they're decent. They're beyond decent. They're excellent classes. So if you're interested in more in cryptography, you're not going to learn how to use the tools maybe exactly, but he does walk through in some of these classes how the tools work and what they do. And it's fascinating, the tools that are out there to help keep your code secure, keep your site secure, keep your network secure. So I can recommend those for you as well. So basically at the end, what you have is a message that's been doubly enciphered with one person's public key and one person's private key. So that's kind of what's going on with public key encryption. DES is still something worth talking about. What DES does is have lots of rounds of running your data through the application. Each round uses a different very large encryption key, and you kind of cycle your way through a 56-bit key to get a bunch of 48s out of it, and you will end up with a horribly permuted piece of data at the end. The public keys, the other examples I've given are all examples of math functions that are referred to as one-way trapdoor functions. It's very easy to move forward in the equation. It's almost impossible to move backwards. So there's safety in using these algorithms, we believe, from the fact that it's countably very difficult to start with the answer and work your way back to the beginning. If you have the keys and you can replay it, then yes. But otherwise, it's tough to do. So one of the side effects is you don't worry about people seeing your encrypted data. So just think about it. With the web page, I open Wireshark, I can see all of your packets coming by, and all of the ones that are sent via HTTPS, I can see them. I just don't understand what they mean because all the data is gibberish. It's encrypted, but I have it. So if I have a tool that can crack it, then I have everything I need. So we're counting on the fact, not that the message is safe because it's clandestinely hid, but that it's very hard to crack the code. That's what we're basing this particular type of security on. AES is another one. One of the interesting studies I've read is, how much would it cost to crack brute force some of these algorithms? How long would it take to use higher encryption at the checkout counter at Target? And if you use a high encryption standard, then it would take 30 seconds for your card to get processed. No retailer would ever agree to that. In fact, Target had a really bad security breach a few years back that cost the CEO his job, and he had chip readers to test, and they took a second or two longer, 3 or 4 seconds longer, for the customers, and they decided they would rather take the risk because they thought they would lose more money putting the chip reading card readers in, and boy, were they wrong. They ended up giving away 400 million people's worth of stuff because people hacked the card readers and they just collected credit card numbers for a year and a half across all of Target stores. And who hasn't gone to Target at least once in a year and a half? Not a huge part of the population. Somebody, if you might trip and find yourself in a Target at some point. Okay, what else did I want to tell you about? Oh, there's a cost of decryption. So what this slide says, it would take a bunch of years to brute force decrypt. And brute force decryption, trying each key, can take 1 second with DES. It would take a lot of years for AES. So I found this spreadsheet that somebody else produced, and it was so interesting that I've kept it. And what this basically came from was a Stack Exchange posting where somebody basically said, here's what a server costs per day, per year, per power. Here's the number of encryptions it can do per second, per year. Here's the cost of electricity. You can put in whatever you want there. And how many decryptions can you do? So with 2 machines and $1,000, you can brute force crack a 73-bit code in a year. If you have an 83-bit code, you'd need a couple of thousand computers and $1 million. So now you're talking about what a government might be willing to put in. If you had a 93-bit encryption scheme, you would need a couple of million computers and $1 billion. Now you're talking about what the United States would do, and $1 trillion and a couple of billion machines if you use a 102-bit size key. The drawback, the flip side of this is it takes a lot longer to check something that was encrypted with that size of a bit, with that size of a key. So it's not like they're all as easy as the other, and the pain is only on the decryption part, the brute force crack part. It's slow the more bits you use to encrypt your credit card number and send it and have the other side decrypt it and get the answer back. So there's balancing that goes on here, which is why all of these exist, and they're not all just using 1,000-bit keys. All right, so that's important to kind of understand as a practical matter. All right, guys, that's what I have for today. I think there's a couple of other interesting things maybe in here in the slides. They talk about modular arithmetic. We've done that already. They talk about RSA in more detail. They do walk through an example if you want to see one that's kind of interesting. And then they talk about securing email and securing TCP with SSL, which is completely obsolete. We use TLS now. Securing web traffic, but we've talked about all of that stuff throughout the semester. You cannot teach a class in networking without talking about security frequently throughout the semester, unless you just want students to fail. But here's the parting thought I'll give you on it. If you try to tackle security on your own, you will fail. There's no maybe. You will fail. Let me give you 30 seconds to tell you how it is that a big security operator will handle protecting a client. Let's say you have a firewall from a company that sells and maintains rules for firewalls. All of their firewalls around the world typically are being managed in real time, and anytime there's an anomaly, it sends enough telemetry about what it looks like and what it is for the supplier, for the person you're paying to help protect you, to kind of figure out what's going on. They'll have engineers dive into it immediately. And as soon as they figure out sort of what's unique about it so that they can recognize it, then they push the fingerprint rule out to all of the customers' managed devices around the world immediately. And they are immediately inoculated against this particular threat. And if somebody else is the first one to get attacked on something, maybe they can stop that before it goes very far and give everybody the rule to block that one. So I don't know about other vendors, and I don't know what percentage of, I don't know how impressive this number really is. I know that it sounds impressive, okay? But Cisco blocks 40 billion attacks a day using that strategy for their customers, not of themselves, for their clients who use their product and subscribe, to having the security knock look at it. So if you try to do it on your own, good luck. It won't work. You'll fail at it. All right, guys, have a great weekend. I will see you in class on Monday. Bye, everyone. Oh, and Jackson, as far as the managed switch, it's totally gray now. What is a switch and what is a router? All switches, all high-end switches, particularly data center switches, have the ability to do lots of quasi-routing kinds of things. They may not run all the routing protocols, but they can do high-speed switching and make use of a routing table. So the simplicity that used to come from choosing a switch instead of a router is completely out the door. You need very intensive expertise and training to use high-end data center switches just as much as you do to use data center routers. So you try to use switches as much as you can because they are still simpler and they have the high-speed bus, but those days are over. So I would say, yeah, there's no escaping needing to know how routing is done in detail, technically, with the ability to program it, just because you're using a high-end switch. I hope that helps. All right, bye, guys.